Hey, this is Leach with Simpson Math, and in this video, we're going to be talking about probability trees and reversing the conditional, or also known as Bayes' theorem. So let's talk about what a tree diagram is, or a probability tree is. So first, tree diagrams, I'm going to go ahead and flip down to what one looks like. It's going to look like something like this, where we have branches, probabilities on the branches, they equal some event, more probabilities, and then we have numbers at the end. Cool. All right, so now that you've seen what they look like, let's just first learn kind of the parameters behind them. So first up, we have our tree diagrams. It's going to show a sequence of events as paths that look like branch of a tree, if the trees were sideways. You could do it vertically, but we typically do them sideways. The ones we're doing today are just two-leveled. So at the bottom, I'm going to go ahead and tell you this. A tree with two sets of branches can be re-expressed as a two-way table. But you could use tree diagrams to represent multiple sequences. In a previous video, we talked about at least one. And in that case, let's say it's like something happened 5 times and I want to find the probability that we have at least one success. Well, that would be a tree diagram with probably like 5 different sets of branches, probably equaling at least like 32 kind of options over here on the end. That's a lot that can get kind of big. But even these most simplest ones can answer some kind of interesting questions, which is this idea of Bayes' theorem or reversing the conditional. All right, so the first branch represents a marginal distribution. It's kind of one, and it's air quote, one variable. So it's the one that's dealing with only one variable. It's not dealing with the other. Because typically then, if the information is presented to us in a convenient way to make a tree diagram, the other set of information that they give us is typically conditional probabilities, some sort of conditional information, conditioning on the fact that one of the marginal situations has happened. So given that fact, what's the probability the next thing happens? So subsequent branches are some form of a conditional probability. In the event that we were talking about with the at least ones, those situations, all those branches tend to be independent of each other. And even sometimes just the same numbers being repeated over and over. But they are technically conditional, and when it's independent, it's really going to be the same values because it won't change from branch to branch. But properly, they are conditional probabilities. One note about each of these branches should always add to 1. So imagine you're wandering through a forest, channeling Robert Frost, taking the path less traveled, and you come upon a fork in the road. That fork might be 2 options, it might be 3 options. Well, from that perspective, you have a little bit of amnesia. It's like, oh, well, it looks like when I'm looking at the path, it looks like about half the people go this way, and maybe a little bit less, let's say 40% go this way, and only like 10% go that way. That path is real hard to see. So you're kind of looking at, I know there's been paths behind me, but at this point, of the people who get here, 50, 40, 10, that adds to 100. So it's always, all the branches are always going to add to 1. Then once you're done with all the branches, we're going to multiply across to produce some joint, aka and probabilities. This is fulfilling the general multiplication rule because I'm multiplying by some marginal, some p of a, and then I'm multiplying it, so this is typically some p of a, and I'll be multiplying it by some p of b given a. If there's additional ones, then it's like the probability of C happening given that these other 2 things have already happened. All right, lastly, all those joint probabilities will add up to 1, and we'll see how that works out. So let's take a look at this question. If you're doing notes or something, I would maybe copy this down because in a second I'm going to annotate on these notes, or not the notes, on the question, just so that we can see where our given information is, what we want to know. So you can always pause the video and copy that down if you need to. This is Stu Dent. So this dude's first name is Stu. His last name is Dent. So student likes to snooze his alarm. Trust me, I do too. He gets up with his alarm on only 10% of days. He gets up with 1 snooze on 60% of his days, and the second snooze on 30% of days. Little just commentary here, not a part of the problem. So luckily, he never needs 3 or more snoozes, as that would make this problem too long. So somehow he has some supernatural ability. I don't know how he does it because I like to snooze. And he never ever presses the snooze for I guess the 3rd time. If it's a second snooze, he will get up then. So lucky him and lucky for us, because that makes the problem a bit easier. So when he does get up with the first alarm, Stu is on time to his first class on 95% of days. Good job. With one snooze, whenever he uses one snooze, he is only on time. He's on time only 80% of those days. And when he uses two snoozes, all two of his snoozes, he's then late. Ooh, I wrote this problem was a bit mean. I'm just trying to emulate how it could be a little, how the question writer could be a bit mean. This time it says that he's late on those days. On 60% of those days, he's late. So the other ones were on time. This one is late. So Mr. Dent is late one day, and his professor snarkily says, or ask him if he hit his snooze one too many times. So what is the probability that Stu got up with his very first alarm? So what I might want to encourage you to do, if you want to, I'm going to be documenting what I know. So you can maybe do that if you want to before I show you. What's my given information? So I see these three numbers. I see these three numbers. What do each of those 6 numbers tell us in probability notation? Like probability of alarm, probability of late given alarm, or what are these things telling us? And then what is the question that we're trying to answer? So if you want to do that, pause it. All right. So let's take a look at what I came up with. So it's process our given information and the question. So he gets up with his alarm on 10% of days. I'm just going to shorthand that and call that probability of alarm. So more formally, it's probability that he gets up with his alarm. I don't want to say all those words. So just probability of alarm. At the end of the day, this notation, in my opinion, is a notation for you and your communication with whoever might be reading your work. So as long as you can clearly communicate what that is, no need to, make it long, or you could, define A equals blah, blah, blah if you're going to be using it a lot. All right. So then he gets up with one snooze on 60% of the day. So that's the probability of first snooze. That's what I'll call that. And then, sorry, a little hiccup. And then he gets up with his second snooze on 30% of the days. Do notice that 10 plus 60 plus 30 adds to 1, or 100%. That better happen, or we'll have a problem. And notice that this is also going to be our first pair of branchings. I did give this to us first, which they typically do. With this, we have a marginal distribution or marginal probability. It's the distribution when it's all of them together, or specifically, we have marginal probabilities. So with it being the marginal probability, this has nothing to do about being on time or late. It's 100% about when he wakes up, with what alarm does he get up. All right, this next paragraph is about him being on time, given the fact that he got up how quickly. So when he gets up on his first alarm, Stu is on time to his first class 95% of days. So notice this is a conditional probability. So this is the probability of on time, given the fact that he used his alarm. Now this is worded in our how our English ears like to hear it. When he gets up with his first alarm, Stu is on time 95% of the times. That makes sense with our ears. We like to hear that first. But in Matthew world, we do write our conditions at the end. What I want to know, given my conditions. Then, given the fact he gets up with one snooze, he's on time 80%. So this would be probability of on time given first snooze. And then with 2 snoozes, he is late. Whoa, he is late 60% of days. So do be careful about that. So this is probability that he is late given that second snooze. So Mr. Dent is late one day. Notice that is my given information. What's the probability that Stu got up with his very first alarm? So these 2 things are in kind of different sentences. One was just kind of a statement of fact, and the other is then the question. But the question is relying upon that information that he was late one day. So I want to know what's the probability that he used his alarm, that he got up with his alarm, with that first alarm, no snoozes, given the fact that he was late. All right. So let's draw this tree diagram out. I have this all done, but I'm going to zoom in on it. I'm just going to talk about it in pieces, so don't try to do everything at once. I just want you to see all the options so you know how to kind of grow with it. Let me get rid of this spell check issue. There we go. Okay, so we're going to work left to right. We're going to start with the marginal distribution. So if you look at the marginal distributions that we highlighted above, we have a trio of branches here. This trio of branches, or not trio, but we have a branch that goes into 3 different branches. It doesn't matter where you put them. I'm just going to put them in the same order that the problem presents it to us, and just kind of in a logical order for us. I am adding this little just note to myself that this column is what he got up with. He got up with his alarm, first snooze, second snooze. So in 10% of times, we're going to travel this path to the alarm. 60% of time, we're going to travel this path to first snooze. 30% of the time, we're going to travel to second snooze. So again, we got that from this paragraph and our given information we've already talked about. Now I'm just documenting it in this kind of visual format. All right, cool. So there's that path. I like to put the probabilities on the line and the events here. I'm going to show you an example from like a textbook situation, and they might have swapped it. It's all good. It doesn't really matter too much, but I like that because it's I'm kind of imagining I'm standing here. I'm seeing that this is a well-trodden path. There's less foot traffic here, and you can barely maybe see the path that way. I'm imagining walking through a woods on a hike. All right, so then now notice the second option, the second variable. I'm calling that variable the arrival status. And you don't have to label anything here. This is maybe something just kind of more for you, just to know, well, what's this, all this column representing? This is all representing our arrival status. So he could be on time to the first class or late to the first class. So I have on time or late for each, and maybe for your sanity, keep them in the same order. Even though they gave us the late for the third option down here, I still have that second there. All right, so then given the fact that he used his alarm, what's the probability that, well, which one did they give us? And I do have them colored, the orange, the red, the pink for the given information. So they gave us this information that 95% of the time when he used his alarm, he was on time. So I'm just going to plop down the 95%. Well, if you knew that 95% of the time he was on time when he used his alarm, how often was he late? Well, among the times when he used his alarm, that would be 5%. So again, notice each of these branches add to 100% or 1. And I'm going to use it as a decimal or fraction, so that way I can just do the math at that level. I don't have to make conversions later. So just to be clear, this 0.05 is probability of late given that he used his alarm. That is not the question. That is not the question that we're trying to answer. The question we're trying to answer is alarm given late. That would be a tree diagram that starts with late or not late, or actually let's say on time or late. And then we have a branching of 3 things after that. That's not this situation. We don't have that information. That's what we're needing to figure out. So just wanted to point out, because sometimes students are like, oh, it's this thing. And it's like, that's the reverse of what we're looking for, right? So now that we have that, let's do this one. Given the fact that he used his first snooze and got up then, what's the probability he was on time? Well, we found out that that was 80%. So then what's the probability he was late? There would be 20%. So 20% of the time when he used his first snooze, then he was late. And then lastly, we're using this last statement here. If he uses his 2 snooze, he's late 60% of those days. So on his second snooze, given the fact that he used the second snooze, what's the probability that he's late? That's going to be that 60%. So when he used the second snooze, that would be 40% of the time of that time he was on time. So just have this note that every branching adds to 1 or 100%. That's how I can get that 0.4. All right, lastly, our joint probabilities. So let's multiply across. So I'm going to do 0.1 times 0.95, which I have documented right here. So 0.1 times 0.95, and we're going to end up with 0.095. So recall to get joint probabilities, we're going to multiply this is our P of A times P of B given A. So we just do that multiplication. And so that's why this is our joint or an and probability. So out of all of his class days, there's a 9.5% chance that I grab a random day And on that random day, he got up from his alarm the first time, and he was on time. All right. So what about this one? So again, I'm going to do 0.1 times 0.05. And when I do that, I get 0.005. Don't worry about this green coloring. We'll use that in a second, along with the purple. But I do have this annotated just for our sake. This is probability of alarm and late. Again, these are our joint and probabilities. So if I select one of his days at random, going to his college class, there is a 0.5% chance, 1 out of 200 chance that I select a day that he did wake up with his alarm, but he was late. All right. So that probability out of all of it is pretty low. All right, so we can finish the rest by multiplying 0.6 times 0.8 to get 0.48, 0.6 times 0.2 to get 0.12, 0.3 times 0.4 to get 0.12, 0.3 times 0.6 to get 0.18. Notice that all of these added up together does give me 1, or 100%. One other thing I want to point out about this, look at these two numbers added together. What does that give me? It gives me 0.1. That is not a coincidence. That happens for every one of these. This adds to 0.6. This adds to 0.3. And the reason why that happens is because remember, each of these branches are 100%. So I'm splitting 10% into 95% of the 10%, 5% of the 10% to give me these two numbers, right? So that's why this is referencing back to that 10%. This is referencing back to that 60%. Those will also kind of make a little bit more sense when I compare this to a two-way table. All right, so again, what's the question I want to find? Probability of alarm given late. So looking at my tree diagram, so now the tree diagram is completed. Where's the times when he's late? Well, I can find the times that he's late this time, this time, this time. I can add up these joint probabilities because these are disjoint probabilities, making this is like another kind of probability model. Again, everything adds here to 1. They're disjoint, so I can just add things up to find these OR probabilities. So if I in this instance, or this instance, or this instant, if I add all those up, that would give me cumulatively all the times that he's late. All right, so if I add those up, that's going to become my denominator, and then my numerator is then going to be this and probability and alarm. I have this documented down here. So the probability of alarm given late is going to be the probability of alarm and late. Sorry, my brain stopped for a second. Probability of alarm and late divided by the probability of late. Remember a little tip I told you, remember this is a vertical line, but oopsie, what if it was a little bit slashed? Don't draw it slashed. But what if mentally it was a little bit slashed? Where this is like a denominator, that is what's in the denominator. Then my numerator is all the alarms that match that situation. So that's why this is my denominator, and then the only one when he wakes up from uses his alarm in that situation is that satisfies my numerator is this 0.005. So I'm going to have my 0.005 over my 0.005 plus 0.12 plus 0.18. That's these numbers right here. So then I end up with my numerator being this 0.005 divided by about 30%. So instead of it being about a 0.5% chance that this happens, it moves it up to almost 1.5, almost 2% chance. So given the fact that he was late, and his professor was a bit snarky, he's like, "Oh, did you sleep through your alarm again?" They have alarms for that. That's so you can be on time. You know how professors can be guilty. I try not to be. So if that happens, what's the probability he goes, "Actually, no, I got up on time. This other drama happened in my life, and I wasn't able to make it. Sorry for being so concerned." So that's where we end up with that. So that's one of those rare instances, but do note that it is notably higher than the and probability because the likelihood that this happens, is a bit low. All right, so I'm going to show you how we can compare what we just made to this two-way table. It's already done because I have it, I have it already written out in advance, so the video isn't any longer than it needs to be. But let's make this comparison. So I'm going to zoom back as much as I can. All right, so Notice here, let's start with this given information of our conditionals. I'm sorry, misspoke, of our marginals. And so notice where that goes. That goes in my total. These are all my alarms, all my first snoozes, all my second snoozes. That's those same numbers right here. And of course, my total totals then add up to 1 or 100%. Then these numbers here, these are my joint or my and probabilities. And so those just go here in the respective spots. Notice this 0.095 is alarm and on time. There it is. This numerator that we have, this 0.005, that's right here, 0.005, that's that and. So when we put those together into our total joint probabilities like that, we end up with these values in those spots. And then of course I can add them up across, just like we did to get this 0.305 for this denominator here. So notice if I have this two-way table, and now from this two-way table, if I said, hey, what's the probability of alarm given late? Was, well, among my lates, everything else is dead to me. What's the probability it's late? What's the probability it was alarm? 0.005 over this. Got it. But notice, in the way that the problem was built out, we didn't have the luxury of kind of plugging in these numbers down here. Because notice, this 95%, 80%, 60% doesn't have a home in this two-way table. We can get that two-way table from this tree diagram or by doing that multiplication. All right, I hope seeing this tree diagram situation helped understand that. Oh, I have one more set of videos. I forgot. All right, that's real quick. Let's talk about this one. A company experiments with 3 website designs to see which one would lead to the highest probability of purchase. The first, design A, used enhanced product information. Second, design B, used extensive iconography. And the third, design C, allowed the customers to submit their own product rating. This is called A/B testing. Well, here we have a C. This is common in website design, especially when you're redesigning, to kind of in a live situation, see how your customers react to minor changes. These tend to be a little bit bigger changes, but often in minor changes to be able to kind of tweak and perfect your websites. After 6 weeks of testing, the designs delivered probabilities of purchase 9%, 3%, 6% rather, and 3% respectively. Equal numbers of customers were sent randomly to each website. Complete parts A through D below. So first we're going to do the table. So notice it says equal customers were sent to each website. So the probability that a customer got design A, 1/3 or 0.333, design B and design C the same because that was equal. Given the fact that they went to design A, 9% of those people made a purchase. So then 1 minus that is 0.91 for the no purchase. Given the fact that they went to design B, 6% made a purchase, 0.06. 94% did not. Similarly, 3% and 97%. And then we multiply these together. We multiply to get the ands, and we do that all the way across, and we get these numbers. All right. Then, what percent of customers who visited the site made a purchase? Well, that's these that I have highlighted in green. They made a purchase, made a purchase, made a purchase. So it's this plus this plus this because it's an or situation. I don't care whether they made a purchase from which design, just what's the likelihood they made a purchase. So total 6%. Notice that this averages out here because it was even, that kind of makes sense. If I average these 3 numbers, I get 6. But if for some reason there was a situation where maybe design A was shown to a lot more people, then obviously it would be closer to that 9%. What's the probability that a randomly selected customer was sent to design C? So this is based on just that given information we already know. No trickery there. Given that a customer made a purchase, what's the probability that the customer had been sent to design C? Kind of wish that this question would have asked what's the probability that a randomly selected customer was sent to the design C and made a purchase, because that would be helpful to identify this 0.010 that we're going to use. But in order to do this given, so this is probability they went to C, given they made a purchase. So this is my denominator, these added together, so this 6% is my denominator. What's the probability they made a purchase? Sorry, what's the probability they had design C? So it's C and purchase. And so we're going to have 1 over 0.06, which is just 1/6 or 0.167. There we go. Now, that concludes this video. Hope this helped you gain an understanding of how to do two-way tables, especially building up our knowledge from our conditionals, probabilities a little bit better. And then this process of reversing the conditional, that's that Bayes theorem. I didn't show you Bayes theorem because it's a really complicated looking thing, but you do it innately from just using that tree diagram. I hope this helped, and I'll see you in the next one. Bye.